First order differential equations. If we take a function such as dy by dx equals 3, and we integrated both sides of that, like so, with respect to x, we'd end up with the equation, the indefinite integral, or the indefinite integral of that would be y is equal to 3x plus c. You all know that. We've done enough work on it now. The constant c is an arbitrary constant and gives rise to the family of curves. Each of the curves, in this case they're straight lines, but we'd still call them a family of curves, being dependent on the value of c. So examples would include y equals 3x plus 8, y is equal to 3x plus 3, y equals to 3x, and y equals 3x minus 4 are examples of the infinite number of curves that could satisfy that equation. And there are those 4 of them graphed. Okay? So, a particular curve of the family can be determined when a point on the curve is specified. So, for example, if it's specified that the function y equals 3x plus c passes through the point where x is 1 and y is 2, then we could substitute those values in for x and y, rearrange, and find the constant c, which is done there. So we've put in x is equal to 1, y is equal to 2, rearranged that equation, and found that the constant c is equal to minus 1. Then we can plot that particular member of the family of curves of y is equal to 3x plus c, the one which crosses through the point 1, 2. Yep, all okay with that so far? So, differential equations. Differential equations are equations that contain differential coefficients. Examples are dy by dx is equal to 7x. It's a first order differential equation. And then we've got d2y by dx squared plus 5dy by dx plus 2y. That is equal to 0. An example of a second order differential equation. The degree of a differential equation is that of the highest power of the highest differential, which the equation contains after any simplification. For example, the second differential is raised to the power of 3. The first differential is raised to 5. It's a second order differential equation because the highest differential is a second differential, d2 by dy dx squared. And it is of degree 3 because the second differential, the highest differential, has a power of 3. Okay? So what we need to do is have a look at how we can solve these differential equations and hence solve problems that involve differential equations in engineering. So, starting with a differential equation, it is possible by integration and by being given sufficient data to determine unknown constants to obtain the original function. That process is called solving the differential equation. Solution to a differential equation which contains one or more arbitrary constants of integration is called a general solution. So that initial equation we had with the plus c is the general solution to that differential equation, dy by dx is equal to 3x. When additional information is known, such as the curve passing through a point or through given values of the variables involved, so that the constants can be calculated, the result is called a particular solution for that differential equation. The proper name given to the additional information which is used to make it a particular solution, are called boundary conditions. So for that initial differential equation, dy by dx is equal to 3, the general solution is y is equal to 3x plus c, and y is equal to 3x minus 1 is the general solution with the boundary conditions that y equals 2 when x is equal to 1. Yeah? All happy and follow that so far? So, let us have a look at solving first order ODEs using what's called separation of variables. Equations of the form dy by dx is equal to a function fx can be solved by integration. With this type of function, it's possible to separate all the y's to one side of the equation and all the x's to the other side. Solving such equations is therefore known as solution by separation of variables. So what we're going to do is have a look at that example on the board there. Determine the general solution of x times dy by dx is equal to 2 minus 4x cubed. Yep. So let's write that out so it's nice and big. We've got x dy by dx is equal to 2 minus 4x cubed. What can we do to arrange that so all the y's are on one side? In essence, what we want is we want this differential on one side of the equation and we want that x over the other side. What's the operation between these two? So we want to divide by x. So dividing by x on this side leaves us with simply dy by dx. And how can I put that on the other side? Two over x is that correct? You've probably gone a step quicker than perhaps I would have done. Does everybody understand that? What's happened here is this in longhand becomes 4x cubed over x, and then these two, one of those x's and that x cancels out. So it is 2 over x minus 4x squared. Yep. All happy with that? Yeah. Now what happens, so this side is that. So what we do now is we integrate both sides. So we do the integral of dy by dx is equal to the integral of 2 over x minus 4x squared. What does integrating this side do? Yeah. And then what's the result of integrating 2 over x? 2ln x minus 4/3 x cubed plus c. Okay, and that is the general solution. Yep. Everybody understand, follow that one. So, find a particular solution of the differential equation 5 dy by dx plus 2x equals 3, given that y equals 1 2/5 when x equals 2. So there are boundary conditions to find a particular solution. So what's the first thing I need to do? Yep, minus 2x, so we end up with 5 dy by dx is equal to 3 minus 2x. Next operation, divide by 5. Yep. Next bit. Integrate both sides. So we end up with y on that side is equal to the integral of 3/5 minus 2x/5 dx. The integral of 3/5 is now that's differentiating where it disappeared. How could we just thinking on the side? How can we put x on 3/5 and it's still equal to 3/5? We could put x to the 0. Yeah, and in the process of integrating 3x to the 0 is we add 1 to the index, multiply by that new index, don't we? Yeah. So we make that 1, multiply that, so it ends up as 3/5 x. Yeah. So the variable comes back basically. Yeah, when you integrate a constant, you just bring the independent variable back. So that is 3x/5, and this one what happens to this one? Two x squared over 10. And can we simplify that? This one? x squared over 5 plus c. So now what we have to do is put our boundary conditions in. One and 2/5 is equal to 3 times 2 over 5 minus 2 squared over 5 plus c. Probably easiest to resolve these before we shift them around. So 1 and 2/5 is equal to 3 times 6/5 minus 4/5 plus c. One and 2/5 is equal to 2/5 plus c, therefore c equals 1. So the particular solution is y is equal to 3x over 5 minus x squared over 5 plus 1. Yeah. This time we've got 2t p minus d theta by dt equals 5, and theta equals 2 when t equals 1. The boundary conditions. So what do we need to do to that? Divide by 2t. So we end up with t minus d theta by dt equals 5 over 2t. Then anyone not see how that's arrived at? If you subtract a t from this side, you end up with minus d theta by t dt. So one way to look at it is to say I'm going to add that to that side and then subtract this from the t, and that's why you end up with those two the other way round. We don't want a negative differential. Yeah. Next thing is integrate both sides, so we end up with theta on this side is equal to the integral of t minus 5 over 2t dt. Integral of t is t squared. Would indeed be t squared over 2. Add 1 to the index, which is 1 in this case, and divide by the new index. And 5 over 2t. Anything missing from that? Anything? Yeah, go on, there's plus c missing. Anything else? Think of this bit as 5 over 2 times 1 over t. Ain't no x's involved. That's a constant, isn't it? So we can take that out as a constant. And then the integral of 1 over 2t is ln 2t. Yeah? All right? So that's the general solution. Particular solution. We've got theta is equal to 2 when t is equal to 1. So 2 is equal to 1 squared over 2 minus 5 over 2 ln 2 times 1 plus c. Two equals 0.5 minus 2.5 ln of 2 plus c. C is equal to 2 plus 2.5 ln of 2 minus 0.5. Am I right? What did that come out as on in your calculator? What we got? 3 over 2. Or 1.5. So, particular solution is theta equals a half t squared minus 5 ln t over 2, isn't it? Oh, hang on. I see what he's done. He's written it out and then simplified it. So let's write it out. Theta is equal to, and we add t squared over 5 turning this general solution into a particular solution. So 5 over 2 ln t plus 1.5. Yeah. Good job you're watching me, innit? Yeah. And then what he's done here, my old friend Mr. Bird in the book, is taken a half. There's a half as a common to those two terms. So he's taken a half outside some brackets and put t squared minus 5 ln t and what he's also done is put the 1.5 in brackets. So what he's done is made that 3. So if you multiply that out, you'll end up with 1.5. Okay? If you had that question in the exam, I'd happily accept that as the right answer. Okay? I don't necessarily see any great advantage in taking that common factor out. Well, yeah, it does, I suppose. All right. Everybody happy? You all got everything you want down from that? Right. The last one we look at before I give you the exercise for you to have a go at based upon this is this one, which has kind of got an engineering flavour to it. Bend a moment m of a beam is given by dm by dx is equal to minus omega times brackets L minus x. So we've got a differential equation here. dm by dx is equal to minus omega L minus x. Omega and x are constants. Find m. In terms of x, given that m equals a half omega L squared when x is equal to 0. Okay? So what's the first thing we need to do? Do you think? Yeah. Is there anything we could do to make that process easier? Expand the brackets. Yeah. So we've got to expand the brackets to dm by dx is equal to minus omega L plus omega x. Now integrate. So we end up with m is equal to the integral of minus omega L plus omega x dx integrating minus omega L. Yeah. M is equal to minus omega L x plus omega x squared. Missing anything? Over 2 plus c. Omega and L are unknown constants. Yeah, and you ain't going to be finding them because you haven't been given any information. It says m is equal to half omega L squared when x is 0. That are boundary conditions you've been given. Yeah. Yeah, I think you're probably right. That's not my mistake for a change. It's the birds. Yeah, there are a few mistakes in the book. Yeah, yeah. I'll not claim otherwise. Okay, so that is your general solution. Okay. And we know that m is equal to half omega L squared, so half omega L squared is equal, m is equal to that when x is equal to 0. So if x is equal to 0, what will this bit be worth? And this bit? So c is equal to half omega L squared. So we can now write our particular solution. M is equal to minus omega L x plus omega x squared over 2 plus half omega L squared. Tidy that up at all? Fully justifiable solution, by the way, that's wholly correct. You'd have to leave this outside, wouldn't you, because there's not L involved in that. Factor of omega out. Yeah, we could do, let's try that. So m is equal to omega brackets minus Lx plus x squared over 2 plus L squared over 2. Agreed? Anything else we could do? Probably not. Right? I'd be happy with this solution anyway. If you got to there, exam question. Alright? But you've not been given value for L, so you're not finding that constant. but you'll just find a particular solution in terms of x. Okay? So, on the next page, there are a number of further practice questions involving solving the first order differential equations. There's a pretty good chance that you'll get something involving solving first order differential equations in an exam paper. So I suggest you get some practice in. If you get stuck on one, give us a shout, come and give you a hand. Okay?